So today, gonna work through correlation stuff. Basically, some sort of basic correlations procedures, some different stuff that we can do. We kind of set up familiarity with covariance correlation models and some of the sort of comparisons of individual coefficients. I'm gonna skip the matrix algebra. It's there if you want to go through and take a look at it, but uh, particularly with just maybe a couple people. And Robert, you're going to be jumping in and out based on other stuff. Okay. So we'll go through and probably make it into some initial stuff on repeated measures, which will be nice. It'll just get us farther along for this. So I'll go through and sort of touch base with you both to sort of make sure that we're sort of on the same page in terms of sort of ideas and concepts. But if I'm working through something and something's not making sense, just sort of jump in and stop me, and we'll slow things down a little bit. Sound good? Cool. All right. So there we go. All right. So correlations. You're both familiar with correlations. Basically, we're just talking about some measure of association, and this starts to become important from a statistical standpoint. Talking about if we're talking about correlations, we're talking about a random variable x and a random variable y. Okay, Matt, do you know? So when I'm talking about a random variable x, random variable y, what are we talking about here?
Is it just that both variables can vary?
Yep, both variables can vary. It's part of it, and sort of by definition, a variable has to vary. If it's all the same number, it's not a variable; it's a constant. Well, we're talking about a random variable. Random variable is the variables that we generally think of when we're talking about sort of sampling variables, right? I've got sort of a big bin of marbles. My random variable, I'm just going through and pulling out uh, sort of things, just kind of not looking in there, going through, and every one that comes out has an equal opportunity to be sampled, right? So let's say, Matt, I've got a jar of marbles. There's 5 colors each. If I am just randomly sort of pulling marbles out, uh, what's what's the likelihood of? Let's say I've got like a 1,000 marbles, right? What's the distribution? What should the distribution be of those 4 or 5 different colors?
You've got 5 colors and 1,000 marbles, so that would be 200 out of 1,000 to 1015.
Yeah, right. So it should get relatively equal numbers of all marbles. So as I'm going through and pulling things out, right? Does it have to be that way though?
No.
No. I could get all greens. Seems pretty unlikely depending on the size of my sample, but that is a possibility in the universe, right? But I'm just going through and I'm grabbing things at random. So if we're looking at correlations, what we're doing is we're looking at some randomly selected variable, random sampling of variable x, random sampling of variable y, and looking at the extent to which those two relate to one another. Essentially, the question we're asking is, does information about a value of x tell me about the corresponding value of y? Okay. Here we're assuming a bivariate normal model, which we'll talk about in just in a few slides. And here, in terms of statistical assumptions, we're assuming sampling error in both x and both y. Okay. So if we're saying that there's sampling error in both x and both y, Robert, do I expect my sample of x to be the mean value of that to be identical to the population mean?
No, there'd be some error.
There's going to be some error. Same thing with y, right? So basically, I'm assuming error on both sides. Okay. Now, correlation from a statistical standpoint has some differences than regression. If I'm talking about regression, I'm talking about a statistical model where I've got a fixed variable x using to predict some observed values of random variable y. So we've talked about random variables. Matt, Robert, either one of you have an idea. What are we talking about when we're talking about a fixed variable?
Would this be like a unit change in x equates to a unit change in
y? Is that kind of what you're getting at?
Well, that's what the regression model is intended to do. Now, you're right, in a bivariate, and we talked about this last week, in a bivariate regression where I have one predictor and one outcome, our standardized regression coefficient is equivalent to my correlation coefficient. It's the same thing, right? Now, my regression also gives me an unstandardized model where I have an intercept and then an unstandardized regression coefficient. And so that's just the predictive approach to sort of this. But when we're talking about any idea what a fixed variable would be, hey, Basha, and how that might differ from what we've already established is going to be the random variable.
Would this be IBDV? I'm taking one more guess.
Yeah, no, it's so basically, if we go back to Matt's jar of marbles, okay? So Matt, if I'm having you pull sort of a random, and let's say that we don't have sort of there's not equal numbers of all 5 different colors. Let's say we've got something that looks like a distribution. Most of them are green. We have some yellow, we have some red, and then we have a small number of blues and a small number of blacks, let's say, right? So really the distribution looks kind of normal, right? And so if I went through and had you go through and randomly pull marbles, you're probably going to get the most marbles of what color? Green, right? You're going to get a few, some of the others, but it's probably, and if you get a big enough sample, it's going to have that nice normal curve, right? That's our random sample. If we've got a fixed variable, what we've done is we've systematically pulled, it's not variable, it's not random. What we've done is we've systematically sampled values to represent the whole range of outcomes. And so what we might do, even though there's very few blacks and very few blues in that distribution, maybe we go through and sample equal levels and we get 10 blacks, 10 blues, 10 yellows, 10 reds, 10 blues, so that we have equal representation of all values or all values in that distribution. Is that a random sample? What do you think?
No.
No, that wouldn't be a random sample. What you've done there is you've created a fixed sample. Fixed sample means that we've gone through and systematically sampled every single value, all relevant values within that distribution, and have them represented in our sample. Okay. Now, is that fixed? If we have a fixed variable, is that fixed variable have a normal distribution? Probably not, right? If we've got equal levels across all, that's not the only way you can draw a fixed variable. But in a traditional regression model, this starts to become important, because a regression model, the technical assumptions of a regression model is that we've systematically selected our predictors and have specifically chosen specific values. And we're looking at the ability of that to then predict random values of variable y. So this is different in the assumptions than a correlation where we have a random variable x and a random variable y. Here we have a fixed variable x predicting a random variable y, and as a consequence, our linear regression model assumes that we only have sampling error in our outcome. Okay, so what I did is I went through and I systematically picked. I didn't go through and randomly grab kids as they were walking across Prexis to be in my sample. I went through and I pulled 20 freshmen, 20 sophomores, 20 juniors, 20 seniors, and measured them all on the outcome. Right, my predictor is fixed, but the values of my corresponding outcome are going to be randomly generated, because I wasn't concerned about what those specific values are. Okay. Questions about this distinction between a fixed variable and a random variable? Okay. Now, and we'll get into this more when we get into regression, do we ever conduct research this way, or are regression models in psychology ever conducted in this way? Basha, you're shaking your head no. Why is that?
I'm
Oh, whoops, you lost ya.
Oh, sorry. I'm not entirely sure. I kind of stepped in when I didn't really know what was happening. So I'm just trying to.
Yeah. So I don't know, Robert or Matt, does this sound like sort of the description of the regression model here with a fixed variable x and a random variable y? Does that sound like how we usually conduct regression models? Probably not, huh? Usually what we do is we just say, here's the sample, right, that we've got. And so my predictors are random, my outcomes are random, right? And so as a consequence, what ends up happening is I'm sort of regressing a random variable y on a random variable x, which is technically a violation of sort of my underlying assumptions. Now we can do things to then go through and make sure our inferences are correct, but it's important to recognize sort of this distinction between fixed variable, random variable, and the implications for distributions and some of that type of thing. Okay. Questions to this point? All right. Cool. So basic correlation stuff, properties of correlation coefficients, bounded by -1 to 1. Okay. Um, uh, as we start to get closer out to those bounds, we get indication of a stronger association as we get closer to 0, suggesting little to no association between x and y, where knowing something about x tells me nothing about the corresponding value of y. Asterisk this, because if we're talking about our standardized regression coefficients, those technically can exceed 1 or -1, not off. It should be something, if you notice that, you should probably sort of double check your model, but it's something that can happen. But our correlation coefficients, -1, 1, those are the upper and lower bounds. And these values very efficiently package the magnitude of the association, how closely these things are related to one another, and then also the direction. Based on that sign. Basha, sort of on your screen, make a motion for what positive correlations look like in a scatter plot. Yeah, that looks good. I'll say sort of as x increases, y increases, correct? Yep. Negative correlation, same way, the opposite direction. As x increases, y decreases. Now, it's important to remember that for psychology, a lot of the stuff that we're working on, the scale is arbitrary, right? Like, do higher levels mean more or lower levels mean more? So the sign is often arbitrary, and so we're generally less worried about the direction of it, so long as we know that it's going in the right direction. More interested in the magnitude of things, but important to know that sort of these are sort of the pieces of information that we get in that correlation coefficient. Okay. So if you want to play around with correlation coefficients, and I encourage you to do so, I guess starting here, Robert, looking at this graph right here, what's the nature of the correlation here between our BDI scores and our CAPS scores here? Positively correlated. If I know something about your increasing BDI score, I expect your PTSD score to increase based on this. Robert, so we see we've got a correlation of 0.54 here. Does that make sense to you looking at that scatter plot? Seems reasonable, huh? And so we see some general, the cloud is going this way. It's sort of increasing, right? But it's not so tight as to expect these things to be unitary to one another, right? So if you want to practice sort of looking at correlations, I would go ahead and click this link down here. Guess the correlation. This is a fantastic online program that will give you scatter plots that you then get to. It's probably the best video game in existence. What you get to do is guess your values for the scatter plot, and then you get scored. You get so many hearts, right? So here I lost all my hearts, right? I had a high score of 30, right? What I had, see, look, I don't know. Maybe this is what I had. 0.7 is a correlation. I don't know. I was off on that. Turns out it was actually 0.13. So I lost on that. But So to go through, play around with it, and people watching the video do that. Post me high scores. What I want to see is turn this into a competition. I want to see what the high score is for sort of guess the correlation. It's surprisingly difficult.
So Josh, I just want to jump in real quick and tell you, in my undergrad, the textbook actually taught you how to eyeball estimate correlations. So I got really good at it in undergrad.
Okay.
So long that I'm no longer very good at it.
Okay, we'll see. We'll see. I'm expecting big things from Dr. Helm right there. So, all right. So before we get into sort of more of the nuts and bolts, want to just do a quick recap on some basic concepts that we covered last semester. First thing is variability. Okay, if we're talking about variability, and again, this is a really, really important concept to sort of have a good handle on. It's surprisingly difficult sometimes, but if we're talking about variability, we're talking about the extent to which scores in a distribution spread out or clustered together. Okay, if we're looking at our figure here, of these scores, Basha, which color graph here has the greatest degree of variability, and which has the least amount of variability?
Would the pink one have the greatest amount of, no, the least amount of variability?
Yeah.
And then the blue?
Yeah. Has the most, right? So we're talking about how spread out these scores are. Okay. Now, if I have all scores in a distribution, I don't have a variable, I have a constant. There's no variability in that. Everything is exactly the same. If I were running an ANOVA model and everybody in my condition A had a score of 15, I would have no variability in that data, and that would sort of potentially cause some problems maybe. Okay. But if I've got a data set where I have large differences between individual scores, I would say there's a large amount of variability in that. So when we're talking about variability, this is just a non-specific metric of the extent to which scores are spread out or condensed together. Okay. We typically have a lot of different indices of variabilities. We have range, standard deviation, variance. All of these describe your distribution in terms of distance. Okay. And we can use these to start to infer information about how much difference would I expect between two randomly selected scores from the distribution, or the difference between, say, the mean of the distribution and some individual and some randomly selected score. So if I have a great deal of variability, let's say going to Matt, so looking at this graph right here, if I were to pull two scores from the black distribution and two scores from the green distribution, on average, across multiple draws, which sets would I expect to be closer together, the blue set or the black sets or the green sets?
Sorry, give me 1 second to make my graph slightly bigger. All right, so comparing black and green. Which ones would be closer together is the question?
Yeah.
Green would be closer together.
Green would be closer together. I got less variability in that in that distribution, right? Now, does that mean for any sort of single draw that the green scores are going to be closer to one another than the black scores? Not necessarily, but over time, there's less variability. There's more stuff going on in that black distribution, whereas I can get sort of scores that are farther away from one another. Same thing I could think about if I were to randomly select a score from the green distribution and randomly select a score from a black distribution. On average, which distribution would I expect those scores to be farther from the mean, which these are all nice and normal, it's right down in the center. Would expect the black scores to be farther from the mean than the green scores. Okay, and if we think back to how we were thinking about this in an ANOVA model, thinking about this as error, right? If my prediction is the mean, right, I'm expecting everybody to fall on the mean. My black distribution is going to have more error than my green distribution because I'm going to have more scores that are falling farther away from the mean than on the black distribution or than on the green distribution here. Okay, so just thinking about sort of different ways to think about variability and how to conceptualize this, right? And sort of thinking about that error piece gets into trying to consider how well some individual score represents the distribution as a whole, thinking about this in terms of error, right? If I were to say, Basha, what I'm going to do is you get to choose a score, and then you guys need to guess and tell me what that value is without looking at it. and I'm going to pay you more money for being closer to the mean than farther away from the mean. Would you want to draw from the pink distribution or the blue distribution?
The pink.
The pink distribution, right? You're never going to be straight on, but you're going to be closer with the pink distribution on average than the black distribution, right? So just thinking about variability and thinking about this flexibly in a number of different ways is really going to start to help as we sort of get into some more advanced models, okay? We also talked about variance. Variance is, remember, statistically, we can describe this as the second population moment. So in terms of describing the distribution of a parameter, mean is the first population moment, variance is the second. Variance is interpreted as roughly as the average squared distance from the mean. We can take the variance, we can take the square root of that, gives us a standard deviation, which again can be loosely interpreted as the average distance of any given score from the mean. Okay, so variance is incredibly important for calculation, but so in terms of intuitive sort of interpretation, not super useful, right? So Robert, if I said, hey, I have a variance estimate of 1,000, is that a big number or a small number? Kind of hard to know, right? Standard deviation gives us something that has a better sort of intuitive value. So I can say, yeah, on average, if you tell me that I have a standard deviation of 5, I could say, okay, on average from this distribution, any randomly selected score is going to be on average probably about 5 units from the mean. Now, does that mean every score that you randomly draw is going to be 5 units from the mean? Nope. But if I go through and look on average, it's going to be about that distance. Okay. Standard deviation also starts to tell us, so to give us information in terms of how extreme a score is. So lots of different things we can go through and use here. Okay. So we're talking about how we go through and calculate this. Okay. Remember that if we're doing this sort of by definition by hand, what we've got is a column of X values. Okay. And the first thing we're going to do is we're going to calculate a deviation score. Anytime I talk about a deviation score, it's almost always going to be the deviation or the difference between some observation and the mean of that distribution. Okay. So what we've done here is we've created a deviation score, and basically we're taking each value and subtracting the mean of the distribution. So I've got -5, 3, -1, 2, 1 here. So we've got our column of deviation scores. Then what I'm going to do is I'm going to square the deviation, take the square of each deviation score. So each one of these, I'm going to take them and I'm going to square them, okay? And then what I'm going to do is I'm going to sum all of those squared deviation scores. This is going to give me my sum of squares, okay? Sum of squares is just the sum of your squared deviations here, and I sum those up, and it gives me a value of 40, okay? So Matt, can you tell me why did I square those deviation scores?
Because the sum of the deviations would be 0.
Yeah, by definition. The sum of your deviation scores need to equal to 0. If they're not, you've done something wrong, right? And what I need to do is I want to add these up to give me a metric of variability, okay? And that's what your sum of squares is. Probably even less interpretive value than your variance, but sum of squares is just a raw metric of variability. So we have sum of squares, variance, standard deviation, all based on the same sort of type of thing. They're just different versions of the same thing, which is some metric of variability in your data set. Okay, so I've got my sum of squares. Then what I'm going to do is I'm going to divide my sum of squares by the number of scores minus 1 to get me to my sample variance. Okay. Bosch or Matt, Robert, it's probably been too long for you, but either Bosch or Matt, do you remember why we divide by n minus 1 instead of just the number of scores in the sample?
So I remember it has to do with degrees of freedom.
Yeah.
I don't feel like that's a very satisfying answer.
Yeah. Anything to add to that, Basha?
Does it have anything to do with like accounting for error? I don't remember.
A little bit, yeah. So what we would do if we were to go through, remember that if we were calculating the population variance, we would just divide by the number of observations in the population, right? So we take the sum of squares divided by n, that's our population formula. But for samples, right, if we're thinking about samples, if I have a nice normal curve, right, a nice normal distribution, and I go through and I just randomly sample scores from that nice normal distribution, where are the bulk of my scores going to come from in that distribution?
The center of the distribution?
In the center of this distribution. And particularly, Matt, if I have a pretty small sample, let's say I'm pulling, say, 40 people out of that distribution, how likely is it that I'm going to catch the folks at the very extreme of that tail?
Somewhat unlikely, right?
Yeah. And so what I'm going to end up with is a distribution, a sample that has pretty much everybody pulled from the center, and I'm kind of missing those low frequency things. And so if I go through and I calculate the variance of that sample, what's that going to look like relative to the population variance? Is it going to be less variable or more variable?
Less variable.
Less variable, right? So what we have is a problem if we've got bias in our estimate, right? So what we can do in a very simple fix is what we do is we take that sum of squares estimate and divide it by n-1, okay? So as my sample gets larger and larger and larger and larger, what's the relative impact on that n-1 denominator relative to n? It goes down, right? If I have a sample of 10 and I'm dividing by 9, that's going to have a much bigger impact on sort of making that estimate larger than if I have a sample of 1,000 and I divide it by 999, right? And so what happens is that as our samples get larger and larger and larger, Basha, what is the likelihood of us capturing those extreme ends of the distribution?
More likely.
And more likely. And so we get something that's more representative. And so that's why we go through in our sample estimate, we divide that by n-1 mathematically. It's a really straightforward and easy way to go through and account for bias so that our sample estimate is an unbiased estimate of the population parameter here. Okay. So that gets us to our variance. And then to get our standard deviation, we just take the square root of our variance. We can move back and forth with this very easily in terms of looking at variance, standard deviation. Standard deviation is really nice because it gives us something that has a little bit more interpretive value, right? So this is on average, this is across the distribution, the average distance of approximately the average distance of any score from the mean of the distribution, but variance is going to be the thing we're probably using more often in terms of calculation and things along those lines, okay? For mathematical, statistical things, you should probably always be using the variance in terms of your calculations as opposed to your standard deviations. And that can start to become problematic for certain types of things, if you remember, okay? All right, so computational formula. This is, I like walking through the definitional formula just because it's sort of a nice way to go through and say, all right, this is from a meaningful standpoint, what's going on with the calculation of this. But if we wanted to just calculate a sum of squares value for the sample, we could also use this formula down here. Mathematically, they're equivalent. Okay. All right. So now that we've got variance understood, what we want to do now is start to add some complexity to this and introduce covariance, okay? Covariance is the degree to which two variables vary with one another, okay? And our formula for covariance is going to be the sum of the deviation scores of x from the mean multiplied by the deviation scores of y for the mean over n-1, okay? And so if I go through and I take a look, and again, we've got our depression and PTSD sort of scatter plot here. What I've got is here's my BDI score, and then the mean value of that represented by this vertical axis, and then my PTSD score is here, and the mean represented by my horizontal axis, okay? And if we think about what we're doing with covariance, let's say I take a score with a large positive deviation from the mean on X, right? So here's my X. So let's say this scores around here are going to have a large positive deviation score, right? If I take this score here and subtract it from the mean, I'm getting a large value, right? And I also couple that with a score that has a large positive deviation from Y. If here's the mean of Y and here's my point, right? I've got a large positive deviation, right? Robert, what do I get if I multiply a large positive variable by a large positive positive value by a large positive value?
An even larger positive value.
An even larger positive value. Okay, so if I'm taking a large positive deviation, multiply it by a large positive deviation, I get a large positive score. What if I flip it around though? What if I take a value that's way below the mean? Okay, so I take an x value that has a large negative deviation score, right? So if I take this value here and subtract the mean, I get a large negative value, but it's also negative with respect to y. So here is a large negative deviation from the mean here. Robert, what happens if I multiply a large negative value by a large negative value?
A large positive value.
A large positive value. And so what we can see here, based on this formula, for something like this, what happens if I've got x's with large positive values, if I've got large x values paired with large y values, the sum of these products are going to be large and positive, but similar for results for small x's coupled with small y's, right? And so what I get is a large positive value indicating a positive covariance between these two variables, right? And we get something like this, okay? Now, on the other hand, if I had a different situation, not the one indicated here, let's say I've got a situation where I have large values of x that are paired with small values of y. So if I take a big positive deviation and multiply it by a large negative deviation, what's my value going to be? Large and negative, right? And same thing if I take a large negative deviations in x and multiply it by large positive deviations in y, going to get a large negative value. And so, Basha, what type of association are we capturing here?
Negative.
Yeah, I'm going to get something that's doing this, right? Sort of the opposite direction. Okay, but let's say I've got a different scenario. In this case, if x and y are unrelated, sometimes I'm going to have large x values paired with large y values, and sometimes they're going to be paired with small y values. And sometimes I'm going to have large y values that are associated with large x values, and sometimes they're going to be associated with small y values. If I take the sum of a lot of large positive values and a lot of large negative values, what's the sum of what's that going to look like? Yeah, I'm going to get something that's very close to zero. Things are going to cancel out. So to my deviation scores of my x and my y, some are going to be large and positive, some are going to be large and negative. Some of them are going to be hanging out all around the mean so that they're sort of small and sort of close to zero anyway. I'm essentially going to get a cloud, right? Where x is unrelated to y. X does not covary with y. Knowing something about x gives me no information about the y is going to be. That's a situation where I have something that would sort of conceivably be close to a zero covariance there, right? And so indicating that I don't have a relation between these two variables. So here's the definitional formula for covariance. Basically, we're taking the sum of these the deviation products and dividing it by the number of people in my sample minus one, or the degrees of freedom. Here's a computational formula that we can go through. These two things are mathematically equivalent, but I like this because if we look at it closely, we can see how this represents what's going on here. In this case, we would probably have some reasonably sized covariance indicating that as x increases, we tend to see corresponding increases in y. And so this is coming together in basically a sort of a raw, unstandardized metric of the degree to which these two variables covary with one another. Okay. I'm kind of seeing where that's coming from. Okay. All right. So if we go through and we calculate a covariance estimate, what we know is our covariance estimate is going to be a joint function of the standard deviation of x and standard deviation of y. The more variability we get in x and the more variability that we get in y, what's going to happen to our covariance? Lets it go up. Okay, this is where when we talk about problems with restriction of range, if I don't have much variability in my x and much variability in my y, there's not much of an opportunity for things to correlate with one another, right? So when we're thinking about covariance and we're thinking about sort of our regression models, sort of the variability of our scores starts to become important. Now, if we're talking about means-based analyses, do we want more variability or less variability in our like sort of traditional experimental types of stuff? Typically want it less, because if we're always predicting the mean value for my condition, if I have a lot of variability, it means that people are kind of all over the place. When we switch over to regression focused stuff, what I'm really looking for is more variability in X, more variability in Y. That lends itself to identifying stronger associations. Okay, but as we talked about, our covariance estimate, important for calculation, but not a whole lot of interpretive value. I can't look at a covariance and say, oh yes, this is indicative of a strong relationship or a weak relationship. And so what we can do is, if we take that covariance estimate and if I divide it by the product of the standard deviations of X and Y, it standardizes that coefficient, and it gives me my Pearson correlation. Okay, our Pearson correlation is just the covariance of X and Y divided by the standard deviation of X times the standard deviation of Y. If I do this, what it does is it goes through and gives me our standard correlation coefficient ranging from -1 to 1, where the sign indicates the direction of the association. The absolute value tells me the magnitude. Okay, and so this is how we arrive at that Pearson correlation. It's not magical. It doesn't come off of eyeballing scatter plots. It's a direct function of our covariance estimate here. Okay. Now, the one thing we need to do, similar when we talked about bias in our estimates, we've talked about last semester, we talked about bias in our effect size estimate of D or G, however we want to talk about it. We've talked about potential bias for a number of different sort of eta squareds and things along those lines. We should recognize that our Pearson correlation is technically not an unbiased estimate of the population parameter rho if we have small samples. Okay, so if I have a sample, say a pilot sample of 20, right, and I look at the correlation between X and Y, the estimate I get is probably going to be an overestimate of what that actual population correlation coefficient is. Anybody have an idea why those, why in small samples your Pearson correlation is going to be an overestimate of the population correlation?
I can try.
Yeah.
Is it because we're not accounting for that variability like we did in that other? I don't know what we were doing.
Yeah. No, that's a good thought, and I like where your head's at. Technically, not really, because remember that our correlations will, if we restrict our variability in our measures, that tends to suppress my correlation, and so, but you're exactly right. If I had sort of something that my sample did not express the full range, then that could cause a suppression of my correlation coefficient. But Basha, if I have only a few sort of but you're on the right track. If I only have a few, let's think about, so I've got my sort of scatter plot of just a few, say 15 observations, right? And let's say, so most of them are kind of hanging out here, but then I did get a sample that had sort of kind of an extreme score, and I got a point that's way out here. What's that going to do to the strength of my correlation?
It's going to make it become stronger.
It's going to make it a lot stronger, right? So with small samples, we can have one point that falls along that regression line that can start to result in a much stronger estimate of that correlation than is perhaps warranted. If we had a much larger sample, now this point is not by itself. It's out here in a larger cloud that kind of gets in there. But if it's just one, it can really start to influence that. And so when we're thinking about our correction for correlations in small samples, and small is same thing with Hedges G. Like, I don't know what small means. It just means smallish, right? So there's no, oh, if it's this point or more. But basically what we can do is we can apply a correction to that. Your adjusted R, or your adjusted correlation here, is going to be 1 minus the square of your correlation times n minus 1 over n minus 2. Essentially what's going to happen is as your sample size gets smaller and smaller, you're going to get a larger penalty to that correlation. As your sample size gets bigger and bigger, the adjustment is going to turn out to be quite trivial. Okay, so just know that for small samples, your Pearson correlation that you calculate is probably going to be positively biased. What I would encourage is sort of maybe calculating that adjustment to your R Pearson correlation. Kind of look at the two to see, so okay, which one of these is a better, more reasonable estimate. Questions on this? All right. So testing these, right? Our for our Pearson correlation, our null hypotheses row, that's that P looking thing there. It's not a p-value, that's sort of Greek rho. That's the representation of your population parameter for a correlation. Our null hypothesis is rho equal to 0. Association with the population is 0. X and Y are independent of one another, linearly independent because your Pearson correlation is a linear coefficient here, right? Your alternative hypothesis, rho does not equal 0. This is just saying that the association of the population is some non-variant 0 value, right? It's a non-directional hypothesis. It could be a positive value, a negative value. And essentially what your alternative hypothesis is saying is that X and Y hold some linear relation to one another. Okay. Now, again, the linear piece is important. Going back to last lecture from last week when we talked about the importance of looking at your data to make sure that, yes, a linear function is the best way to represent that association, because sometimes it won't be. But if we're looking at correlations, remember that what we're looking at here are linear associations between two variables. Okay. Sampling distribution of our correlation coefficients. Assuming the null hypotheses, we follow a t-distribution. Okay, t-distribution, you know the t-distribution, you all love and are really good at the t-distribution. What we would do, so when you go through and calculate a correlation in SPSS and it gives you a p-value associated with it, this is what it's doing. Basically, if we take our correlation and multiply it by the square root of n minus 2, and divide that value by the square root of 1 minus the square of our function, the square of our estimate, that's going to give us a t-statistic. Okay, so if, assuming that X and Y have no association in the population, we've got assuming that the null hypothesis is true, the distribution of our correlation coefficients is going to follow that nice t-distribution that we all know and love. All we need to do then is take that estimate, turn that into a p-value, and then look at that against your critical value for t with n minus 2 degrees of freedom. Okay. People seeing how we get at sort of this formula here? And then at that point, you're getting a t-value that you plug in with the corresponding degrees of freedom, get a p-value, and that's sort of all you need to do to test this. Questions? All right.
Yeah, go ahead.
No, go for it, Matt.
So I was going to ask if you can use Excel to calculate p-values like you could the t-test. Would you use the similar Excel sheet previously?
Yeah, you can.
Or would you need a new one?
No. And so I went through and posted your first problem set online on the thing yesterday. I'm going to have you doing some stuff to play around with that if you want to. And yeah, you can go through and indicate the degrees of freedom in the P for that, and sort of all that sort of goes through. So you can do it in Excel, or if you don't want to sort of go through and sort of take the time to code that in this, I mean, it's not going to take but 2 seconds if you understand what you're doing. But I can also just go through and calculate it by hand, take whatever the t-value is, sort of plug it into your p-value calculator, your t corresponding degrees of freedom. Again, that's n minus 2, and get it. So a lot of different ways you can go through and get that. But yes, you're exactly right, Matt. You could set this up very, very easily in an Excel calculator. Questions? All right. So the nice thing about R is we can also use R as an estimate of our effect size. Okay. And R is really, if we're looking at a lot of meta-analyses, R is a nice general metric of effect because we can use other metrics of effects and translate that into an R to start to compare effect sizes across various different types of analyses. Okay, and again, what R is doing is giving an estimate of the magnitude of a relation in the population. How closely are these two things related to one another? Okay, standard benchmarks for small, medium, and large associations: 0.1, 0.3, 0.5. Okay, so Robert, do you remember what the correlation between BDI and CAPS was in that graph that we showed?
It was like 0.534 or something.
Okay, so and so based on our benchmark, how would we qualify the magnitude of that association?
That would be medium. Wait, was that D or R?
So here's our benchmarks for Pearson correlation: 0.1, 0.3, 0.5. So BDI and PTSD were correlated 0.535 or something like that. How would we qualify the magnitude of that association?
It was large.
Large, right? We've got a strong association. And Robert, based on your understanding of depression and PTSD, does that make sense? Yeah, sure does, right? So again, the low bound of our association, a correlation of 0.1. Emily, if you saw that two things were associated 0.1 with one another, would you be super impressed by that?
No.
Probably not, right? But this is consistent with a small magnitude correlation, something that's sort of detectable, but probably not something we would notice just sort of by looking at it, right? And so, but it's still kind of that lower threshold for a small effect. So if I've got a sample that's really large, you start to get in for correlation samples of around 400 or something like that, you can start to identify these correlations as statistically significant. Okay, but Basha, what's maybe my concern with identifying sort of a correlation as statistically significant? What does that technically mean?
It means that there's some potential like association or difference, but we don't know for a fact what that.
Yeah. Anytime we reject the null hypotheses, if I just say, hey, I've rejected the null hypotheses 99% of the time, what does that mean?
It means that it's just a non-zero value.
Yes, absolutely. Do I really care in all cases whether or not a correlation is exactly zero? No, right? And so this is the thing we have to start sort of keeping in mind. So I'm reading a paper and they say, oh, we found a significant association between X and Y in my sample of 5,000. All right, well, fine, but does that mean anything, right? I could actually kind of care less. So you have evidence that your correlation is not zero, but what does that mean? How large is it, right? And so sort of needing as we go through and start working through these analyses to be thinking, always keeping in the back of my mind, thinking about sort of the meaningfulness of this, right? So is a correlation of 0.1, is it meaningful? Maybe or maybe not, right? If it's large scale stuff, if I'm looking at the relation between number of cigarettes a day smoked and throat cancer, probably, right? Like anything is probably not good. And on that scale, it's going to be sort of a big deal. But sort of in other situations, maybe I don't care so much. Okay. So always keeping that in mind. So R is a nice magnitude of effect size. The nice thing is R and D hold a direct relation with one another. Okay, and I can go from R to D and D to R really easy, right? And this starts to become helpful if I'm reading papers and someone reports from a means-based analysis an R value as a metric of effect. That's fine. It's not necessarily the most intuitive for sort of a means-based comparison. I might want to think about that in terms of standard deviation difference. But the nice thing is as long as they did that, I can go back and forth between R and D to get it into the metric that makes most sense to me, right? So if I want to calculate D and I have a Pearson correlation, I can take 2 times my correlation over the square root of 1 minus the square of my correlation, gives me approximation of D. If I have R, I can translate it over. If I have a D and I want to get it in OR, I take my d divided by the square root of the square root of the square of my d plus 4 gives me r. I can move back and forth with this to go through and make sure that sort of things are sort of lining up the way I would like, right? And so in a meta-analysis, if I've gone through and I have some studies that measured this association through independent sample t-tests and some of it that measured the association based on a correlation, what I can do is I can put those all in the same metric and compare and kind of look at what those effects are looking like. Yeah. Another thing we can do that makes R super handy is I can square it, and it's going to give me an additional effect size metric. My squared correlation can be interpreted as the proportion of variability in Y that's attributable to variability in X. Okay. Emily, last semester, when did we talk about something that sounds kind of like this interpretation of the squared correlation?
Sounds like variance.
Okay, yeah. And what other metric? Do you remember what metric of effect size we were talking about last semester? Where we were talking about proportion of variability?
No.
Basha or Matt, do you remember?
So I want to say it was the effect sizes in ANOVA, like omega squared and stuff like that.
Yeah, for our eta squared, right? So I've got a grouping factor, right? I've got a condition, a 3-level, I've got an experimental condition that's got 3 levels. And what I do is I find sort of in my ANOVA, I find evidence for differences somewhere across those 3 groups. But my eta squared was my omega squared was my effect size that says my categorical variable accounts for 15% of the total variability in my outcome. Same thing here. Here with our Pearson correlation, what we've got is a continuous X and a continuous Y. And what it's saying is sort of giving me the overlap of these 2 variables that variability, we'll say, let's say I've got a medium effect. So I've got an R squared of 0.09. That's telling me 9% of the total variability in Y is attributable to variability in X. Now, there's some causal language that you could infer there. Don't. It's just saying that these 2 things vary with one another such that knowledge or sort of information about variability in X will give me information about 9% of the account for about 9% of the variability that I'm seeing in Y. Okay. So, but this is really easy. All I have to do is take my Pearson correlation, take the square of that, and that converts that to a proportion of variance effect size that sort of starts to have quite a bit of intuitive meaning. Okay. Questions about this?
So I have one question.
Yeah.
On the slide, it is a lowercase r squared. I've seen it as capital R squared before. Are those the same thing?
So if we're talking about capital R squared, what we're generally talking about, although notation isn't consistent across the board. Generally, with capital R squared, we're talking about that tends to be referring to like regression-based models where we've got a multiple R, right? So we've got one outcome and multiple predictors. Here we're just talking about the bivariate case, a Pearson correlation that we're squaring, and so that's why I've got those in lowercase. You've just got this is representing just the bivariate case. As we start to get multiple predictors and regressing an outcome onto multiple predictors, how that variance is shared starts to shift around. And so generally, if that were the thing that we're talking about, that's where we would use the uppercase R for that.
Thank you.
But Matt, know that if there's one thing you've probably identified, at least in this sort of through this class, that people are not consistent in notation. So just be aware that there are a couple of different ways to think about that and talk about it. All right. So our assumptions. Matt, this starts to get into black holes, potential black holes in multivariate space here. Okay. Starts to get a little bit difficult to wrap our head around. Okay. So all of our inferences of our Pearson correlation as an estimate of the population association based on the assumption that my variables are sampled from a bivariate normal distribution. Okay, so I go through and I get Emily, give me two variables.
Gender and major.
Okay. I don't like either of those. Give me two continuous variables.
Continuous variables. Okay.
How about this? Okay. We'll conceptualize appropriately. So gender as a continuum of masculinity to femininity.
Cool.
Okay. And then give me another random variable or another continuous variable. Income. Okay, sounds good. Okay. My assumption, so if I look at the correlation between gender is measured as a continuous construct and income, right? I can calculate a Pearson correlation. But the extent to which that Pearson correlation can be sort of interpreted as an estimate of the population coefficient, right? The extent to which in the universe gender identity is associated with income. What we're assuming is that these two variables are coming from a bivariate normal distribution. All right. And when we start to get into sort of this understanding of a bivariate normal distribution, what we have to do is we're out of one-dimensional or two-dimensional space, and we start getting into three-dimensional space and trying to think about what's going on with these distributions. So when we're talking about bivariate normal distribution, and this is an important concept to understand, particularly as we get into regression, bivariate normal, if we've got a bivariate normal distribution, first thing we need to think about are the marginal distributions of x and the marginal distributions of y. Okay, marginal distribution of x and marginal distribution of y just says that if I plot my x value, if I plot the distribution of my x and I plot the distribution of my y, I'm just going to get a normal distribution with both of those variables. Okay, so to this point, all through 50/60, when we're looking at distributions of scores, we're looking at marginal distributions there. Okay. So if I just go in my SPSS set and I sort of create a histogram of x, create a histogram of y, that's my marginal distribution. And if I've got if my distribution is bivariate normal, it's saying that, so I'm assuming that I got a normal distribution of x and normal distribution of y. Okay. Comfortable with that?
Clarify, yeah. The marginal distribution are basically the univariate distributions of each of the variables.
You can think about it that way, yeah. Okay. But here's the wrinkle. What we need to do when we start thinking about these associations, we start to introduce a concept where we're talking about our conditional distribution of x and y. Okay. And so what the conditional distribution of x and y, this says not only if I look at x and plot that out, I get a normal distribution. I look at y and I get a normal distribution. Okay. But also what I need to see is that for any specific value of y, say, so I'm not going to look at the whole sample. I'm only going to look at cases with a y value of 5. If I were to go through and plot out the distribution of x for all cases with a y value of 5, I would still see that those x's are normally distributed. Okay. And so in our graph here, in this mesh graph, if I were to go through and say choose y values of -1, if I were to sample all x values that corresponded to a y value of -1, I would still need to see that follow a normal distribution. Okay, so this is different than the marginal distribution. Marginal distribution is all x's in the set, all y's in the set. Each one of those is normal. All right, we all got that. Our conditional distribution says that also what I need to see is that for any value of y, the x's are all distributed. Same thing, let's say I go through and I take a slice here through this mesh at y equal to 1. If I were to do that, I would still see normal distribution of x values. Okay, and then what I'm going to do is for all values of x, the distribution of y is also normal. So here, if I were to go through and cut a line at x equal to 0 and look at, sort of think about this as a cross section, I would see all values of y having a normal distribution. For x equals 0, all values of y have a normal distribution. If I were to go through and slice it as at x equal 1, still having this normal distribution here. Okay, so think about this. These are conditional distributions because it's the conditional distribution or the distribution of x conditioned on some value of y, or the distribution of y conditioned on some value of x. Okay, now I've got this asterisk because, again, when we started to go back through and we were talking about sort of the difference between correlation and regression. For a correlation, for my correlation to be valid, I'm assuming a bivariate normal distribution, which assumes a conditional distribution of both x and y. Now, for regression, my distribution of y for any x is normal. That doesn't hold, right? I don't have conditional distributional assumptions of y conditional on x. Okay, technically. But when we get into regression, we actually will need to assume a bivariate normal distribution because we violate sort of other assumptions. So technically, we don't have an assumption about the conditional distribution of y values in regression, but by definition, we end up having one because we violate stuff in other areas. Okay, but if we're just talking about correlations, this is part of the assumption of the complex distributional assumptions of x and y if we're going to sort of attach strong meaning or interpretations to that coefficient. Okay, so people sort of kind of get the idea of conditional values or the marginal distributions and conditional distributions. Okay, this is sort of comes from sort of high school and middle school drafting for me. But if I'm trying to think about at least sort of project things into three-dimensional space, right? If I do this, everybody sort of throw up one finger. Okay, this is one axis. Throw out your thumb. Now you've got two axes. Now you've modeled two-dimensional space. Okay, throw out a third finger straight out. Nope, in right angles with one another, Basha. You're not in right. If we do this, now I've got three-dimensional space right here, right? I've got an x-axis, I've got a y-axis, and I've got a z-axis, right? And so what I can do is I can start to think about bivariate normal distributions within this three axes, right? And so if we go through and we do this, and we think about this, if we think about under the null hypothesis, right? If we're assuming x and y are unrelated to one another, what would be the shape of a binomial of the bivariate normal distribution under the null hypothesis? As a hint, so we've got our graph here. This is a bivariate normal distribution, but it's a bivariate normal distribution that's inconsistent with the null hypothesis because we can kind of see that we've got an association here. If x is unrelated to y, what would be the shape of that bivariate normal distribution? What would it look like?
Would it be flat?
Not flat necessarily. What do we got there, Robert?
Just trying to say two-dimensional, but
not two-dimensional because we've still got three-dimensional space. Think about if we took a bowl of sand or something, so a funnel of sand, and just had it drop on the ground. What would that distribution of sand look like? One grain at a time falling down. What would that end up looking like?
It would pile up.
Yeah, it would kind of pile up, sort of symmetrical. It'd be kind of circular on all sides and sort of come all together up to the top, right? And so you can think about a bivariate normal distribution under the null hypothesis. That's what this is going to look like, right? We've got a not a cylinder, but sort of an evenly distributed, sort of kind of coming up to sort of a top there. As we start to get relations, an association between X and Y, that sort of completely circular sort of mound that goes out starts to become elongated out, sort of indicating an association. Okay. But if we were to go through and take that null distribution, again, we've got sort of a funnel of sand, and we just hold it up sort of grain by grain, it all falls and sort of spreads out evenly in all directions. If we were to slice that distribution in any way at any point, it would look the same all the way around. That's essentially what we're talking about in terms of a null distribution in bivariate space. Okay. Does that kind of help kind of see what's going on versus here where we very clearly have an association between X and Y? We're seeing sort of this kind of sort of coming into like a narrow ridge, right? This is indicating sort of an association bivariate space, whereas if it wasn't, so we just get that sort of even spread in all directions. Okay. Does that kind of help visualize some of this a little bit better in terms of what we're thinking? Okay. All right. So Pearson correlation in SPSS, this is easy. You just go through, analyze, correlate, bivariate, and we're just going to get correlations here. Okay. So here we've got correlations between PTSD and social support. Emily, what's the correlation between PTSD and social support here?
Is that like the okay, so PTSD and social. So is that the 1 or is that the negative 0.274?
Okay. Yep, negative 0.274. Okay.
Okay.
Okay, so we've got here, and so it's the same thing here. What we've got is looks like a small to moderate association between the degree to which people feel supported by friends, family, significant others, and their PTSD symptom scores here. Okay. Basha, that's a negative association. So what does that mean?
Means it's going this way.
Means it's going that way, right? What else how else might we put that into words?
What were the two variables again? I'm sorry.
Yeah, perceived social support and PTSD scores.
So would it be with more? No. Oh yeah. It'd be more perceived social support would mean less PTSD.
Perfect. Yeah. As and remember that an association is just that. It's not saying causal. So X could be Y, Y could be X. There's no directionality in terms of like sort of what's causing what, right? But what we can say with confidence based on this on these data is that we have evidence for as perceived social support increases, we tend to see a decrease in PTSD symptoms. Alternatively, as PTSD symptoms increase, we tend to see a reduction in perceptions of social support, right? We're not saying why that is. There's no causal language in there. That's just sort of how these two variables, how these two indicators are covariant with one another. And then we have sample sizes and our p-value here, sort of indicating sort of strength of evidence and things like that. Here is Pearson correlation in Stata. This is none of you all are Stata users, but Robert is, and Ali will be. Simple command here, pw core, and then your variables, and then comma sig will just give you p-values with that. All right. Let's do this. Let's take a break and jump back on, let's say at 3:30. So it's not quite 10 minutes, but sort of take a break, jump back on 3:30. Now that we have a good understanding of covariance, correlations, and kind of what this all means, we can start talking about different things that we can start to do with these coefficients. Okay. Sound good? All right, cool. See you in just a few. All right. Thanks everybody for jumping back on after a short break. Any questions about any any of the concepts that we've Bossy, your dog wants to learn about correlations. They're a statistics fanatic, and don't deprive them of that, please. Any questions on the stuff we've covered up to this point? Okay, cool. All right, so we've talked about correlations, covariance, and sort of some of the concepts there. We're going to spend the rest of this lecture or this set of slides talking about some different things we can do with those correlations. So one thing that we can do is we can compare independent coefficients that are pulled from presumably different populations. Null hypothesis in this case is rho 1 minus rho 2 equals 0, right? Essentially what we're saying is the difference in population coefficients is equal to 0, right? Or alternatively, association in population 1 is equal to the association in population 2. Okay, so in this situation, let's say, Emily, you're looking at the correlation between um, uh, uh, ADHD behavior scores, hyperactivity scores, and um, uh, child sex, right? So we're saying like sort of looking at child sex and ADHD, sort of Achenbach checklist, something like that, right? Or no, scratch that, get rid of that, not true. Let's say that we're looking at the association of ADHD scores and ratings of peer liking. Okay. So what you do is you look at that association in boys because a lot of ADHD stuff is looking at boys. So we're looking at symptoms and peer liking in just boys, right? But then maybe the question is do we see the same association? Does that generalize to girls, right? And so maybe we measure the same two variables in girls. And maybe the question is are these two things, or do we have evidence of similar associations across these two populations, right? Now, there are better ways to do this, but one way you could do this is you could run sort of a correlation in this population, and then you sort of run a correlation in another population and see if those two, you have evidence for differences across those. Okay. And so the null hypothesis would be that yes, the association of X and Y is the same. Alternative being no, if I take the correlation population 1, subtract it from population 2, I get some non-zero value, right? Suggesting that there is some difference in these population coefficients, or that the population coefficient population or the coefficient population 1 is different than the coefficient population 2. Okay, so what we're doing here is we're comparing two independent correlations. Now the problem is that the distribution of sample correlation 1 minus sample correlation 2 is complicated. It doesn't follow a nice normal distribution. And remember, if we're going to run inferential tests, all of our inferential tests are predicated on the assumption that we know what the distributions of scores look like under the null hypotheses. Okay, so if we're saying independent sample t-test, we're looking at the mean of this population versus the mean of this population. If the null hypothesis is true and the mean of those populations is actually the same, if I take samples of a certain size from those populations and subtract them, sort of go through and run a calculated t-statistic, that t-statistic follows a normal t-distribution if the null hypothesis is true, right? And so we can use that to start assigning probability values of obtaining data of this nature or more extreme based on sort of the known distribution. Problem is R1 minus R2 doesn't have a nice distribution, which complicates sort of our ability to go through and run that analysis. So what we do instead, if we want to run this, is what we first need to do is perform what's known as a Fisher's R to Z transform. Basically, we're taking that correlation estimate and we're turning it into an alternative metric. And it's pretty straightforward. We'll call the R is what we get out of this. We'll call this R prime. R prime is just 0.5 times the natural log of 1 plus your correlation over 1 minus your correlation, that absolute value. Okay. And if we do that, what we can then do is we know that the distribution of R prime is approximately normal around the population coefficient with a standard error equal to 1 over n minus 3, or 1 over the square root of n minus 3. Okay, so what we can then do is we can use our z statistic, or we can calculate a z statistic based on these R prime coefficients that we've gone through and calculated. Okay, so what we can do, if I say I've got R1 and R2 and I want to see whether or not they're different, I can't do that directly. But if I go through and I take R1 and change it into R prime, and R2, change it into R prime, then what I can do is I can take those values and calculate a z-score for it. And here we're just taking R prime 1, or R1 prime minus R2 prime over the square root of my two standard errors here, 1 over n1 minus 3 plus 1 over n2 minus 3. This gives me a z statistic. And then can we assign a p-value to z statistics? Yeah, all day long, right? Gives me a z-value, and then I just sort of look at the z-value and use an online calculator or my table to go through and so find the p-value associated with that z. Okay. People see the process here?
I just have a quick question. I think
Yeah.
you already said it, but I might have missed it. Why are we doing n minus 3?
Because if I go through and I take my R value and I transcribe it into R prime, and then I go through and I look at the sampling distribution of R prime, the standard error of that sampling distribution is equal to 1 over the size of the sample minus the square root of the size of the sample minus 3. That's just the standard error for that. Okay. So what we do is, because we have two samples, remember this, basically it's like you're running an independent sample t-test, except with correlations, right? Instead of comparing means, you're comparing correlations, right? Because we've got two sources of error. We've got error in the sample 1 and we've got error in the sample 2. That's why we're seeing two sources of error here in the denominator. But Basha, just think about this as the correlation equivalent of a t-test, looking at this correlation between X and Y in this population, correlation of X and Y in this population, and seeing if we have evidence that they're different than one another in the terms of magnitude. Does that help? Okay, cool. Questions about this? All right. And again, we just take the test statistic we hear and evaluate it against a critical value given whatever our alpha is going to be. Generally, it's going to be 0.05, but again, we just get that z-score, and we all know how to get p-values attached to z-scores, easy peasy. Yeah. Can't do this in SPSS to my knowledge for Stata users. Again, this is going to be talking to Robert and Ali if they're watching this video later. Pretty easy to go through and do this just in Stata. If you load the command CORTESTI and then enter the correlation sample for correlation for population 1 or sample 1 and the sample size, correlation for population 2 sample size, it'll go through and run this for you. So here we're wanting to compare. We've got a correlation of 0.45 with a sample of 104 in the first one. Compare that against a sample correlation of 0.53 and a sample of 87 in my second one. If I load this up, it gives me a z statistic of negative 0.714, a p-value of 0.475. So, Matt, what would I conclude, at least in terms of my null hypotheses based on that test?
So we're based on the null hypothesis, we have evidence to suggest a non-zero difference.
It suggests a non-zero difference?
In any case.
So my p-value is 0.475.
Oh. I didn't realize that was a p-value.
Yeah.
My brain's in a strange place. I didn't realize that was a p-value.
Yeah.
I thought it was a
critical value? Yeah. Okay. Nope. So no, that's our p-value. And this is Stata. It's a notation that you're not haven't been exposed to necessarily. So our p-value is 0.475. So what is our conclusion here?
we do not have enough evidence to suggest a non-zero difference.
Yeah, we would fail to reject, right? So based on the data that we have, we don't have evidence to provide, we don't have strong evidence for, or clear evidence of a likely difference in these correlations. Now, 0.45 is definitely a smaller number than 0.53. And we don't have, I mean, these aren't huge sample size, but they're all right? But we're still not seeing enough evidence that what we're doing is we're actually capturing different population parameters across based on the samples that we've got here. Okay, so people kind of understand what we're doing with this test. All right. So another thing that we can do, and we don't do this a whole lot, right? So if I go through and just run a standard test of my correlation, I'm testing whether or not I have evidence that my correlation is different than what number, Emily? Just in my general test. If I say that if I just say I've got a significant correlation, what does that mean?
Less than 0.05.
Okay, well, for my p-value, but in terms of the association, sort of I have a significant correlation. What does that mean?
I guess like close to 1 or negative 1.
Okay, so that would be the max. If I'm reject the null hypothesis and I say that I have a significant correlation, what does that mean, Basha?
It means you have a non-zero difference.
Yeah, it just means that there's not the coefficient, that we have evidence that the population coefficient is likely not zero, right? Is having a correlation that's not exactly zero informative in a lot of situations? Probably not, right? But that's generally what our test does. But it doesn't have to. We can set up our test to test it against any null value that we like, okay? So let's say I'm calling my shot, right? I'm going to say I'm going to make a big money move and say, like, I don't care that my correlation is not, whether or not my correlation is zero is really inconsequential. It doesn't mean anything, right? But what I'm saying is that my association between this new measure that I've created and some outcome, it's going to be a better predictor of this outcome than sort of the existing thing. And the existing thing meta-analysis says that the correlation between sort of existing measures and this is 0.3. I'm thinking this is going to do better. And so what I'm going to do is I'm going to test my correlation not against zero, but I'm going to test it against 0.3, right? And if my thing is done what I think it's doing, I should get an evidence that this correlation coefficient that I get is some value that's potentially bigger, higher than 0.3. Basically, I'm calling my shot. I'm saying, like, I don't care about zero. I'm going to set my null hypothesis up to test against some some predetermined reference value. Think about this as similar to your single sample T, right? You can set up your single sample T or your single sample Z to say, so the null hypothesis is that this is equal to 100, right? I'm saying it's not. I can go through and set that up. We can do the same thing with our correlation coefficients here. So the alternative, or the null hypothesis, is that the association between variables in the population is equal to some reference value. Alternative is that it's some other value than the reference value. How sort of has some questions about the extent to which this can be useful, but I don't know. You know, when we talk about, when we went through all that stuff in terms of talking about the problems with null hypothesis testing and Meal's paper on the paradox of sort of why in social science, as our methods get better and better, and our samples get more and more precise, it makes it easier to reject the null hypotheses versus in physical sciences and physics and things like that. It starts to become harder. That's because in physical sciences, they're often working with a point estimate. If my theory is correct, the result should be this number. And if it's not, then I'm wrong. This is a situation where you could conceivably set something up. If you have good a priori reason for saying that, hey, in general, this is what this coefficient should be. I'm saying it's going to be more or less. Call your shot and just say, so you can run a test against that. pretty straightforward. Here, you're just creating a z-value. Again, you're creating a Fisher R to Z transform for R, Fisher R to Z transform for whatever your reference value is, and then taking that over the square root of 1 over n minus 3. Essentially, again, what you've got is you've got a single sample t-test with, except you're just using correlations here. Okay. So if I wanted to set up a test of whether or not my coefficient was not different than 0, if it was different than 0.3, easy enough to do. Questions here on this? All right. Last thing we can do here is we can start to test whether or not test differences in dependent correlation or in dependent correlation coefficients. And what this is situations where we have coefficients that share some common measure. Okay, and this adds a little bit of complexity into the whole thing. So let's say, Amanda, give me a construct or a measure that you're interested in.
Sorry, it was cutting out. You said just a measure of interest?
Yeah, a measure or a construct of interest to you.
Sure. With jury decision making, I guess we measure, right, whether or not they think someone's going to be guilty of their verdict.
Okay, so sort of how about this? Let's say level of confidence in sort of guilt. That's a nice sort of 0 to 100, not at all, 0% confident, 100% confident. Okay, and then just knowing some of the stuff that you all look at in your lab. Let's say you want to look at that and compare that and look at correlations of confidence with, let's say, conservatism and scores on the modern racism scale. I don't know, right? So these are just sort of variables, right, that sort of work in sort of that stuff. So what you've got is you've got a correlation of confidence with conservatism. You've got a correlation of confidence with modern racism, right? And maybe you want to see whether or not does confidence hold a stronger relation with conservatism versus modern racism. Okay. Well, can we go through and can we just sort of compare those two correlations using the Fisher R to Z like we did before? Nope, because they share a common measure, and that complicates some things, right? And it's all pulled from the same sample. What we can do is start to go through and run some formula that take into account the intercorrelations between all these variables to provide an actual test of the extent to which X is more strongly related to Y versus Z. Okay, so in this situation, your null hypothesis is the correlation of X and Y minus the correlation of X and Z is equal to 0. Alternatively, sort of the correlation of X and Y is equal to XZ. Difference in population correlation for X and Y and X and Z is equal to 0, right? This is all sort of setting up an equivalence. Alternatively, we're looking at the difference in population coefficient for X, Y, and XZ is some non-zero value, or that the population association of X and Y is not equal to X and Z. Okay, so we've got a situation here where we've just got one sample, and we're looking at the correlation of one instrument with one variable versus another. And what happens is that we've got some interdependence with this that we need to sort of start to take into account. We can also use this procedure to look at the extent to which sort of maybe some measure of X and Y is correlated at time 1 with a correlation at time 2. We've still got some dependencies here. In reference and reading materials, you've got materials in the Steiger text or the Howell text, that Steiger article, and then an article by Meng that walks through procedures for how to go through and do this. Now, Howell and Steiger are equivalent procedures. They'll get you, the formula is a little bit different, but it'll give you mathematically equivalent scores. Meng is a little bit different, but the benefit of Meng is it also sets up some opportunities to do some contrast coding with sort of more than two variables, and which is pretty cool. So we'll definitely need to go through, read those resources and get a sense for this, because this is something you'll want to, I'll have you be doing in this problem set that we have out right now. Okay. Questions about what we're doing here and how we're setting this up? Okay. Anybody here have any interest in like measure development or anything like that? Psychometrics or anything ish? Okay. So if let's say I wanted to test convergent discriminant validity of some measure or score, right? I could use this to say, well, if my sort of understanding, if my conceptualization of this variable is correct, scores should correlate more strongly with this construct than with that construct. This is where we would be starting to go through and work through that stuff. Okay. All right. Confidence intervals for correlations. Okay. Again, let's say, Amanda, that I run a sample, I get a correlation of X and Y that's 0.35. How confident am I that that is the actual population coefficient, that the actual association out in the population is actually 0.35?
0.35 is closer to 0, but it's not as much.
Okay. Well, in this situation, right, it's just an estimate of the magnitude of the relation. So sort of whether or not it's closer to 0, farther away from 0, it actually does make a difference, and things start to get squirrely as you get closer to the ends. If you approach a Matt-Helm singularity on either ends, then things start to get a little bit tricky. But sort of in general, we would think that, okay, this is our sample estimate, but if you were to go through and run a separate sample, do you think the correlation would be identical, the same 0.35 number? No, right? It's probably going to jump around a little bit, right? So just like anything else, what we can do is we can start calculating confidence bounds around our point estimate to give us a sense for, all right, what are data supported values for the population coefficient here, right? We talked about how the Pearson correlation on its own is a little bit tricky, but again, what we can do is we can use that Fisher R to Z transform to turn that correlation into R prime, and then start to do some stuff with that. Okay, so what we would do here is we can go through and calculate our confidence interval around rho prime based on our estimate. So what we would do is we would take R prime, so we take Fisher, do the R to Z transform with that, and get a value for that. And then we would go plus or minus whatever our critical Z is for whatever value confidence bound we wanted to collect. Let's say we wanted a confidence bound for a 95% confidence bound. What's the Z value for a two-tailed test for alpha equal 0.05? Does anybody remember? Yeah, 1.96, right? So if I wanted to create a 95% confidence bound, I would take R prime plus or minus 1.96 times the square root of 1 over n minus 3. Okay, so it's the same process we've had. We've got our point estimate plus or minus a critical value times the standard error estimate gives us a confidence bound. Okay, now the trick here is that we're going to get, is that going to give us a confidence bound around my Pearson correlation? Nope. It's going to give me a confidence bound around my R prime value, right? Which isn't what we want. But what we can do is we can back translate those R prime values back into R values, which then will give us sort of our upper and lower bounds for our confidence bound, right? And the formula for upper and lower limits to back transform those into lower and upper bound estimates of the population correlation is just going to be R equals root base E to the 2 times R minus 1 over base E 2 times R prime plus 1. You just back translate that to get your upper and lower values of your correlation coefficient. Okay, so it's just basic algebra, plugging things back and forth. You can, so this is how you would do it by hand. SPSS in one of their various upgrades, which is commendable, now allows you to calculate confidence bounds around correlations within the system, which is nice. Here you just go to analyze, correlate, and then you're going to choose bivariate with confidence intervals if you have sort of the most recent version, and then you just plug your stuff in. Here we go. So here we're looking at the CAPS and the so looking at the relation between social support and PTSD. Matt, I'll ask you because I know your screen is larger. So what is the correlation here between PTSD and social support?
Okay, let's see. Correlation between social support and PTSD. Negative 0.274.
Yep. And what are the lower and upper bounds for that estimate?
Lower is negative 0.372. Upper is negative 0.170.
Yeah, perfect. So SPSS will now do this for you, which is nice, but I am a strong advocate for knowing how to do it by hand, because here you now have to have all the raw data. Here, if someone just reports a Pearson correlation, you can go ahead and calculate confidence bounds for that to see if, let's say, Amanda, you go through it and sort of there's a study out there that looks at a correlation between X and Y. You run your thesis, you get a correlation from different correlation of X and Y, and it looks like it's quite a bit different. I don't know. Calculate a confidence bound around that original one and see how close you are with that. Is this completely implausible, or are you actually kind of consistent within that, right? Starting to help me get an understanding of, am I way off base of what this other thing has, or am I within sort of what we would expect near data supported values of the previous thing? So having a system to do it in our own data is nice, but being able to crank that out by hand is also valuable in a lot of situations. Same thing in Stata. Number of different ways we can go through and do this to get our correlations. It's just PW core and then your variables gives us our correlation coefficient. And then a couple of different ways you can do it if you have the data available to you and you're using raw data, use CI2 and then the two variables, comma core, and this will give you your point estimate and then your upper and lower bound, which is the same thing that we found in SPSS. If you're just in Stata, you can also, if you just don't want to do it by hand, you can command CII2, sample size, correlation coefficient, and then core, and then it'll sort of just calculate that. That's just based on whatever you input there. So a couple of different options with Stata. You're not users, but someone who will be watching this eventually are. So just a couple of different options there. All right, questions up to this point? Okay, power analyses. If you want to determine the size of your sample required to adequately power a test of correlation between X and Y, pretty easy to do in G-Power. Here, all we're going to do is you're going to go up and select exact as the test family, statistical test, correlation bivariate model. Enter you want a two-tailed correlation or a two-tailed test. Enter the correlation that you're hoping to detect, alpha level, power, the null value that you're comparing against. This is almost always going to be 0. And then you go through and hit calculate. Okay. So basically what G-Power here is saying that is if I want to, I'm saying for my study, I'm expecting a correlation of between X and Y of 0.3. And I wanted to sort of say, how many people do I need to identify, sort of reject the null hypotheses at alpha equal 0.05, power equal 0.80? G-Power is saying I need at least 84 people in my sample to reject the null hypotheses at least 80% of the time. Okay, so things are pretty straightforward for testing power of correlations in G-Power. questions with this? All right. Okay. Now we're getting into the good stuff. Okay. So up to this point, we've been talking about Pearson correlations. Okay. And we're talking here about the correlation of the association between a continuous X and a continuous Y variable, right? Emily, this is why I said I didn't like the variables that you gave me after I asked you for variables. And I'm like, no, I don't care for those variables. So you're giving me some categorical variables, right? Which is technically a different form of a correlation than if we have two continuous measures. But the nice thing, if we're looking at correlations, categorical variables get tricky. But if I've got dichotomous variables, right, categorical indicators that are coded 0, 1, I can start to run those and sort of run some equivalent correlations. Okay, so the first equivalent correlation we're going to work through here is what we call the point by serial correlation. Point by serial correlation is the test for the association between a dichotomous X and a continuous outcome. Okay, so if I have a dichotomous variable and a continuous variable, what I can do is I can run a point by serial correlation, and that's going to give me the association between my dichotomous categorical variable and my continuous outcome. Okay. Now the nice thing is my point by serial correlation is mathematically equivalent to my Pearson correlation. They're interchangeable. They're the exact same thing. They're going to give you the exact same value. Okay. So in this example that I have here, what I'm interested in is I'm, again, sort of pulling this from sort of data we have back. What I'm interested in is, so we've got community members coming in following a significant motor vehicle accident. And so what we've done is we've measured their PTSD symptoms. This is the caps here on the horizontal axis or on the vertical axis. And then what we've got is we've categorized people into whether or not they're experiencing chronic pain. This is a big thing for people who have been in accidents is post-accident, do I have prolonged struggles with chronic pain, right? So we've got some people in the sample who don't experience pain, some people who do. Okay. Now, what I can do here, so I've got a dichotomous variable, pain status, yes, no, continuous outcome, PTSD. What I can do is I can just run a correlation between those two, and it's going to give me the association between chronic pain and PTSD, at least based on estimates in this sample. Okay. And Amanda, looking at this, what's the correlation between pain status and PTSD in the data that I have here?
I think that says 0.379.
0.379, right? So I've got a moderate correlation between pain status and PTSD. Amanda, tell me exactly what's going on in this with this correlation. What is this correlation telling me?
So for pain status, is 0, no?
Yep.
Okay. So it does seem like there's more pain, like people with higher levels of PTSD have more pain.
Right. And so we can interchangeable, so we can talk about it this way, or that we could just say just more succinctly that PTSD is associated with pain status such that individuals with chronic pain appear to be experiencing higher levels of post-traumatic stress disorder, right? And so our p-value is very small here. Again, this is a large sample. We have a medium effect going on here. So everything we need to know all kind of captured within the context of this association. Okay. And what we know here, if we go through and we take a look at this correlation, what we see is this. Now, Basha, do you like this scatter plot here?
No.
Nah, it kind of sucks, right? I mean, we've got everybody lined up on one and lined up on the other. So it doesn't have the nice interpretation of that sort of nice continuous measure. But what we know is if we go through and we run a regression line, a line of best fit through that, what it's going to do is find that when X is equal 0, when we're talking about people with no pain, our expected value is going to be the mean of Y for that group. And when for people who do have pain, that line is going to go through the mean for people with chronic, the mean PTSD score for people with chronic pain. And so what we've got is this regression line. If we were to run this in a regression format, what we've got is this line sort of registering, predicting mean values of PTSD for people with low levels and mean values of PTSD for people with chronic pain here, right? So it's going through both of those means with this, okay? What I can do with my point by serial correlation, if I square that, same thing too, it tells me the proportion of variability in my continuous y that's attributable to my categorical x variable, right? So in this situation, someone tell me what's someone square 0.379 and tell me what to get.
0.144.
0.144. So basically what I would say there is that based on these data, I expect chronic pain status to account for about 14% of the total variability in PTSD symptom scores, which is sort of notable, right? We've got a medium effect that sort of we can see, and we would say sort of based on Cohen's benchmarks, we'd talk about a medium effect as something that is sort of visible to the naked eye. I could sort of see if I start seeing people, I could say that, yeah, it looks like PTSD severity is related to chronic pain status, such that individuals with chronic pain tend to have higher levels of PTSD. Okay. You'll kind of see how we're sort of working through sort of this point by serial correlation. Okay. Now, the other cool thing is, or sort of the nice thing about my point by serial, the test of my point by serial is identical to my test of R. Again, it's just a t statistic working again with a n-2 degrees of freedom with this. So again, to calculate t from my point by serial, just take my point by serial, multiply it by the square root of n-2, take that over the square root of 1 minus the square of my point by serial, gives me a test statistic, and then I just evaluate that against a critical value or a critical t with n-2 degrees of freedom. So the test is the exact same thing as the Pearson correlation. Again, these two correlations, these two coefficients are functionally equivalent. Okay. What we also know is our point by serial correlation has a direct mathematical relation to our independent sample t-test. So if I go through and I calculate my independent sample t-test, I can take that test statistic and translate it into a point by serial correlation. If I take the square of my test statistic and divide it by the square of my test plus the degrees of freedom, I get the square of my point by serial correlation. If I want to take the square root of that, that gives me my point by serial correlation. I can move back and forth between my independent sample t-test and my point by serial correlation seamlessly. They're mathematically equivalent to one another. Okay. And so what this means is that my interpretation of my means-based test and my point by serial correlation are interchangeable. If you say, if I've got a dichotomous variable and a continuous variable, I can model this probably as an independent sample t-test, because that's what we did last semester, and that kind of makes more sense. I can talk about this in the difference in my outcome across group 1 and group 2, right? But I can also talk about it as the association of my grouping variable with my outcome variable, and I can model it as a correlation, right? My p-values are going to be identical, right? It doesn't matter. It's only based on how I want to talk about it, right? So I could say that men and women are different in weight, right? I can say that on average, men have greater mass than women. Or I can talk about this as the association between sex and weight, or sex and mass. Doesn't matter. They're the exact same thing. I can talk about this as a linear relation between sex and weight. I can talk about physical weight as varying with gender. I can talk about men being different than women. However I want to do that, it's all the same thing. It's just sort of how I want to present it. Okay. So people see how the point by serial correlation and our independent sample t-tests are essentially just sort of different cases of one another. Okay. And if I go through and do this in SPSS, point by serial correlation in SPSS, I just sort of get it the same way I would get any correlation. I drop in my my dichotomous variable and my continuous outcome. So here I've got participant sex and CAPS 5 total, and I see that at least in these data, sex is unrelated to. I have very little evidence of an association between sex and PTSD. Okay, but if I go down through and I run this as a t-test, looking at mean differences in PTSD across men and women, and I go down, and if we go and see, so my p-value for my correlation is 0.084. If I go down through and I take a look at my p-value for my t-test, it's 0.084. It's the same thing, right? They're interchangeable with one another. So the only thing that influences which one of these tests that I use is whatever I want to, however I want to talk about it. But if I wanted to, I could take that t-value and transform that back into get this correlation value. I can move seamlessly back and forth between these two. Questions? Do people understand sort of the equivalence of this, because it starts to become important in sort of thinking about as we move into things, talking about generalized linear model, about how these things all relate to one another. Okay, cool. Same thing in SATA. If we run our correlation between sex and CAPS total, we get this. If we go through run a t-test, the p-values the exact same. Everything's sort of even Steven. So we can go through and sort of report these however it makes sense, because from a statistical standpoint, it makes no difference. They're the exact same thing. All right. The other thing, and this might not come as a shock, if our point by serial correlation is functionally identical to mathematically equivalent in my t-test, I should be able then to go through and move back and forth between my point by serial correlation and my D effect size. I can move back and forth here. It's the exact same thing as previously with my Pearson correlation, being able to move back and forth between these different metrics. So if I have a biserial correlation, I want to calculate a D statistic. It's just going to be the degrees of freedom of first sample plus the second sample, degree of freedom between my samples aren't going to differ because they're sort of this same for both measures, right? Times my square my point biserial over sample sizes times sort of 1 minus my point biserial. So we can go back and forth and translate that. And what I can then do is I can start to calculate confidence intervals for this D statistic using the T statistic associated with my point biserial here. So let's say, okay, Emily, you've got a paper that you're looking at, and someone's reported a point biserial correlation. But what you really want, and it's just the point biserial correlation, that's all they've given you, right? It's 0.35, okay? But what you want is you want to get a D metric estimate, and then you want to calculate a confidence interval around that, right? With just knowledge of the sample size and the magnitude of that correlation, what you can do is you can take that point biserial correlation and convert it into a t-test, right? With the corresponding degrees of freedom. And then with that test statistic, you can get upper and lower bounds for your non-centrality parameter, like we did last semester. And then you can take the upper and lower bounds of that non-centrality parameter to get upper and lower bounds of your D, right? And so you can go through and use this to sort of put this into whatever form you want to that makes the most sense for the arguments that you're trying to make and the things that you're trying to communicate. So with very little effort, you can move back and forth between this. And again, this isn't just a parlor trick. It's something I do all the time when I'm looking through stuff and I'm like, boy, I want to see how that compares to this. Being able to move transition between these different statistics is very, very helpful based on secondary analysis of stuff. Questions about this? All right. Okay. Phi coefficient. So we've talked about our Pearson correlation. We have continuous X, continuous Y. We talked about our point biserial correlation where we have a dichotomous X and a continuous Y. But let's say we've got a situation where we've got a dichotomous X, dichotomous Y. What we now have is a Phi coefficient. Okay. But the nice thing is phi is also mathematically equivalent to our Pearson correlation. Exact same thing. Okay. Now, the sampling distribution of our phi coefficient is a function of a chi-square with a 1 degree of freedom. Okay. So my phi coefficient, if I have a chi-square, a 2 by 2 chi-square, and I take the chi-square from that test statistic and divide it by my sample size, take the square and take the square root of that, that's going to give me a phi coefficient. So I can move back and forth here. A phi gives me phi is going to be, the phi coefficient is going to be your effect size for a 2 by 2 chi-square analysis. Okay. And again, as with the point biserial and T, interpretation of your phi coefficient and your 2 by 2 chi-square is going to be interchangeable. We can move back and forth with that. Okay. And so we can think about that chi-square, that 2 by 2 chi-square, as an association between my dichotomous X and my dichotomous Y. This is how we would think about it if we're talking about things in terms of phi, or if we're talking about a chi-square, we're talking about the independence of my dichotomous X and my dichotomous Y. But it's all the exact same thing. We can move back and forth and talk about this however makes sense given our problem. Okay. And so once again, in SPSS, calculating my phi coefficient directly is the same way I would calculate a Pearson correlation or a point biserial correlation. I just correlate here, over here. I just want to look at here the correlation between sex and PTSD diagnosis. Okay. And have gotten that here in my correlation table. And it looks like those two things aren't. The correlation, the phi coefficient, which SPSS is reporting as my Pearson correlation, which is fine because it's interchangeable, is negative 0.014. Or I can go through and run this in SPSS as a chi-square, right? And here's going to give me my 2 by 2 table. If I go down through and I look at my significance, my p-value for my chi-square is 0.79. Look down to the p-value for my phi coefficient, 0.79. It's all the same. I can do it however I like. It makes no difference here. Okay. So more. Oh yeah, and then if we want to do this in Stata again, PW core, gender, CAPS diagnosis gives me my correlation and my p-value, or tab gender, CAPS diagnosis, and then add this chi-square at the bottom at the end of that gives me my chi-square coefficient and the p-value. Things are interchangeable with one another. Okay. So moral of the story is anytime I'm wanting to look at an association between a continuous X and a continuous Y, a dichotomous X and a continuous Y, or a dichotomous X and a dichotomous Y, they're all variations on the Pearson correlation. They're all identical to one another. We call them different, sort of technically. The dichotomous X and the continuous Y, we call that a point biserial, and the dichotomous X, the dichotomous Y, we call that a phi coefficient. But mathematically, they're interchangeable. Point biserial interchangeable with independent sample t-test, phi coefficient independent or interchangeable with a 2 by 2 chi-square, right? Now, so basically, anytime we're wanting to look at any combination of dichotomous and continuous variables, this is the stuff that we're using. Okay. Questions on this? All right. Now we do have other coefficients, okay, that require sometimes a little bit more sort of stuff to go through, sometimes not. If we're talking about biserial correlations, similar to our point biserial, but here the assumption is whatever my underlying assumption, or I'm assuming that whatever I've measured as a dichotomous X is part of an underlying sort of continuum, right? So let's say I've got a variable that, Matt, let's say I'm looking at extroversion, okay? and I have this, for whatever reason, someone's measured this as high and low extroversion based on whatever criteria, right? We know that extroversion is not a dichotomous construct, right? It's not like high or low, it's a continuum, right? If all I had was the dichotomous code on that, what I might run is a biserial correlation, because the biserial correlation makes some adjustments that assumes that whatever my dichotomous variable is, there's an underlying continuity to that construct. And so it'll go through and do that. So clinical folks, the same thing. Emily, let's say that I have I want to look at the relation between ADHD diagnoses and peer liking, right? Well, ADHD diagnosis is a arbitrary construct where we're saying that you've met some criteria, right? Point biserial would take into account that sort of conceptually we're thinking about this as a continuum, okay? So I'm making some adjustments there. Tetrachoric correlations, these are going to be similar to phi coefficients, but again, we're assuming underlying continuity in both x and y. So we've got two variables that are dichotomous, but we're saying that these really aren't dichotomous constructs. These aren't categorical constructs. They represent a continuum. A tetrachoric correlation makes an adjustment sort of that assumes underlying dimensionality between those two. Okay. Spearman-Rowe. Here we're applying a Pearson formula to ranked scores. So it's not a real continuous variable where everything is equally spaced. We're just saying that 1 is bigger than 2 is bigger than 3 is bigger than 4. Technically, we would use a Spearman-Rowe with that. And then Kendall-Tau, we got chi-squares, sort of different things. In the handouts folder of the WILE courses, I've got a worksheet that I adapted from Dr. Steve Bieber here when I was an undergrad. I just think it's fantastic. It just got different coefficients talking about the type levels of measurement that are most appropriate with those. So definitely go through, take a look at those and be aware. Pearson correlations are nice, but sometimes it's not the most appropriate coefficient. Again, given those underlying assumptions of bivariate normality, right? Sometimes that's not the case. Sometimes the things that we're measuring aren't continuous data or dichotomous data. Sometimes there are other things. So again, just focusing on that level of measurement is a big piece of choosing the right analyses for the job. Yeah. Questions on any of this? Okay. Feeling okay with correlations? Who knew that you could do so many things with correlations, and correlations were so exciting? That's right, no show of hands, because none of you did. I just sprung this on you and you're all kind of floored. I can see that, okay? So here, jump in. The rest of it is sort of matrix algebra stuff that is cool for some reasons, but we won't spend time working through that. What I do want to do with the rest of our time is start to get a head start on some repeated measures ANOVA stuff. Okay. For our repeated measures designs, I've gone through and switched this up. Usually what I did when I first developed 5300 was we would start with correlations and then go into regression models and then talk about moderation and mediation and then some ANCOVA types of stuff, and eventually did repeaters measures stuff at the end of the semester. But given that you just all came off of 5060 and have some of those means-based analyses more still fresh in your head, students made the strong recommendation to go through and do that first. And so that's what we're doing here, okay? With this set of slides, what we're going to do is we're going to sort of just, again, touch on those means-based analyses. And what we're going to get through today is starting to talk about an introduction to repeated measures designs and how we set these up. These are very, very powerful and very, very cool and useful designs in psychological research, but there's a number, they're more complicated, there's just more things to keep track of, right? And so wanting to make sure that people have a good understanding. Again, I said it last semester, I'll say it again, any opportunity you have to include it or repeat it, to include a repeated measures element into your thesis, dissertation, anything is a good idea, just because these are much, much more powerful and much, much more efficient designs. The cost is that it comes at sort of additional complexity. So you want to make sure that you understand what's happening with these. Yeah. So as an overview, we're talking about our basic ANOVA structure, right? The idea is that we have some hypotheses about differences that we expect across two or more populations, right? Now, we don't know what the population means are across these three different, the population means are for these three different groups or communities. We can't measure that directly. So what we do is we go through and we sample from each one of these, right? So I've got a sample of 15 from population 1, a sample of 15 from population 2, a sample of 15 from population 3, right? And what I go through, and if I go through and measure whatever outcome I'm wanting to measure across each of those samples, I find that I get slightly different values for those mean scores, right? And so two possibilities here, right? I'm seeing these the differences in these means because of just sort of random sampling error, right? Even if population 1, 2, and 3 all had exactly the same mean value in the actual population, I'm going to see some differences in my samples just because of sampling error, right? So maybe what I'm seeing here is just sampling error. I don't know, maybe if I redid this again, sample 3 has the highest value and sample 2 has the lowest. I don't know. They're always going to shift around a little bit, right? Or maybe what's happening is maybe the differences that I'm seeing are being driven by differences in the population means, right? Maybe population 2 does have incrementally higher mean values than population 3, right? And the reason that we're seeing the sample value is higher than the sample value of sample 3 is because those populations do actually differ in sort of whatever it is that we're measuring, right? And so this is our one-way ANOVA. This is where this comes in to try and sort of start to tease this apart. Okay? Our hypotheses, remember for our one-way ANOVA, is that our null is that population mean 1 equals population mean 2 equals population mean 3, right? Means the population from each sample we're drawing are going to be equal, right? If I want to talk about this in terms of linear model terms, I can say that there's no relation between whatever my categorical variable x is and my outcome. Okay, that's an efficient way to go through and talk about this in terms of associations. But sort of my alternative hypotheses, here I'm going to say at least one population mean differs from the others, right? Alternative, I can say sort of I have evidence to suggest that the data are unlikely assuming equal population means. If the samples from each, the populations from each one of these samples were drawn, if they were all identical, it would be unlikely for me to see the data that I've seen. Okay. Now, Amanda, why don't we have something in the slick statistical notation for my alternative hypotheses here?
You don't know like which of the three are different from the other.
Yeah, I can't say that 1 is not equal to 2 is not equal to 3. That is a version of my alternative hypothesis, but there are others, right? All we know based on our omnibus test is that there's a difference in there somewhere, okay? And so we have to just say that out in words, okay? Our F statistic, remember for ANOVA, is looking at the variance between samples over variance expected if the null hypotheses were true, right? We always expect there to be some variability across my across my sample means. What will start to get me a large F test is if my between sample variances starts to exceed what I would expect just based on general sampling error with things, okay? So again, I've got two sets here. I've got set 1 and set 2. Matt, which one of these sets do I have more which one of these sets is showing more variability?
Set 1.
Set 1, and how do you know that?
Because the sum squared, or the variance is higher for set 1.
The variance is higher for set 1. Yep. But if I'm looking at the mean, what are you seeing across sort of the mean differences across these differences in means for set 1 versus set 2?
So the difference between the first mean, second mean, and third mean set 1 is about 5. Difference between the first, second, and third is 2 and 1, so 1.5 approximately for averaging.
Yeah, right. So here in set 1, we've got a difference somewhere between 10 and 15 units, right? Differences in set 2 max out at 3 units, right? So assuming that these are all sort of on the same scale, we're seeing greater differences in set 1 than set 2. Now, to just talk about these in differences is hard because we've got more than 2 groups, but what we can do is look at the variance or the variability in means across these samples and use that as a sort of singular estimate of the magnitude of difference. So correctly identified that we have more variance or more variability in the means in set 1 versus variability in set 2, which is telling us indirectly that there are more differences. There are more mean-based differences in set 1 versus set 2, right? So again, just looping back in and wanting to be very clear about how we're thinking and using and conceptualizing variance as a measure of differences, as opposed to being restricted to just the two case test, or talking about sort of difference in means and things like that. Yeah. People remembering sort of how we're thinking about this. All right. So again, with our one-way ANOVA, what we want to do is we want a partial variability in the sample data to look at systematic effects across our groups. And what we're going to do is we're going to partition variability into between treatment variance and within treatment variance. Okay. We're talking about our between treatment variance. Different reasons why we can see differences between groups. Like one, we can see differences are caused by treatment or group effects, right? I'm seeing differences in my sample 1, sample 2, sample 3 because they're drawn from different populations. I'm seeing differences in my sample means because whatever manipulation I've administered is driving some difference across those means, right? So I've got an actual effect to be found here, right? I can also see differences due to non-systematic differences, just kind of random stuff, right? I'm seeing differences in my sample means because of experimental error, just individual differences, just stuff that comes up. This is just kind of sampling error. I can see systematic differences in my group means because of just other things that I haven't measured, right? Remember, in an ANOVA situation, anything that I haven't measured that's driving variability is by definition error, right? Maybe I have sort of sample 1 is different than sample 2, not because of that they're in population 1 or population 2, but for some third unmeasured variable that's not in my model. Who knows, right? But what I want to do is I'm interested in trying to see where that between group differences is happening, okay? So Basha, where are we seeing the between group differences in this example that we used from last semester, looking at the impact of temperature on learning performance?
We don't see any differences between treatment 1 and treatment 3, but there are differences in treatment 2.
Okay, where are you seeing that happen?
I'm looking at means.
Yeah, right there. Okay, so what we're doing is we've got, if this was just 2 groups, we just look at a difference. That's easy peasy, right? And then we're just running a t-test. But here we don't. We have 3 conditions, right? And so we don't have a single difference metric that makes a lot of sense. But what we can do is we can talk about variability in our group means. If I have larger variability, it says I got more differences. If I have less variability, it means I have less differences. Okay, so my differences between group, my between treatments variance, this is looking at sort of the effect that I'm wanting to get at, plus some sort of other stuff that's going on. Okay. We contrast this against our within treatment groups, or our within treatment variance. Again, if the only thing that's driving differences in whatever outcome I'm interested is because of sort of this grouping variable, then everybody in the same group should have the exact same score, right? Amanda, if your experimental manipulation is the only thing that's driving confidence in guilt, right? Sort of based on jury instructions or some evidence presented or something along those lines. If your if your experimental manipulation is the only thing that determines people's confidence in guilt, then everybody who is in the same condition should all have the same score, right? Because your manipulation is accounting for 100% of the variance in your outcome. Does this ever happen? No, it doesn't, right? We're always going to see some differences within our individual conditions or in our individual groups, right? And because of that, that's suggesting that there's some differences that we're seeing within scores within a condition. This is a product of either some random function or some random influence or stuff that's not measured, right? It's something that I haven't quantified within the context of my analyses, and so by definition, it's error. It could be sort of just random stuff. It could be individual differences. It could be experimental error. It could be something systematic. But if I haven't modeled it, it is by definition error. Okay. So Amanda, where are we seeing our within group differences in this table here?
You would look at just all the scores within like temperature 1, within temperature 2, and within temperature 3.
Yeah. This is my
treatment.
Yeah. This is sort of the differences, the variability that we're seeing in scores within groups. This is our measure of error, right? Because by definition, any differences that we're seeing has to be due to some unmeasured stuff. So that's all sort of error variance, okay? And so what we do then within our ANOVA model, remember, is what we want to do is we want to calculate our F statistic by comparing our between treatment variance over our within treatment variance. Conceptually, what we're doing here is we're looking at observed group differences across my samples versus differences that I would expect given the null hypotheses, right? Essentially what's going on, if the differences that I'm seeing across groups are about the same as the difference that I'm seeing within groups, then it's saying that the differences that I'm seeing across groups are no greater than the differences that I'm seeing within groups, which is not going to be indicative of evidence for systematic differences in the respective population. Yeah. I can also think about my F ratio. As remember, we're talking about the variability that we're seeing across groups is going to be a result of systematic effects, right? Because there really are truly differences in the population, plus some random differences and other sort of stuff going on, right? Versus the stuff that's going on within treatment, that's just error. That's just random differences, right? And if I cancel out random differences with random differences, right? Hopefully what I'm going to get is something that is sort of giving me a higher F value, okay? So if there are no systematic group differences, everything that we're seeing across groups is entirely due to error, then probably I'm going to have random differences over random differences. I'm going to get an F value that's pretty close to 1, right? And I'm probably going to fail to reject the null, right? However, if I do find at least some of my between group differences is due to some systematic effect, what I'm going to have is systematic differences plus random differences divided by random differences. The random differences are going to cancel out, and what I'm going to be left with is some effect that I'm getting, resulting in a ratio that's higher than 1. And hopefully, if it's big enough, so I can go through and say, okay, this is sort of evidence for differences somewhere in my groups. This coming back to people in terms of the conceptualization of these one-way ANOVAs and sort of thinking, understanding conceptually what's happening with these analyses. Okay. All right. Our ANOVA formula. Remember, in our ANOVA table, we've got a lot of different components. We've got our sum of squares total. This is all the variability in the sample. Okay. This is the sum of the squared deviations of person I in group J from the grand mean. We square that deviation, sum them all up. This is just all the variance in the model, right? If I were to just go through and say, in my whole set in SPSS, calculate the variance of my outcome, that's my that's variability that's represented by my sum of squares total. Okay, and remember that sum of squares is just the sum of squared deviations, right? It's just an alternative metric of variability, right? Sum of squares, variance, standard deviation, they're all different versions of the exact same thing. It's just variance, okay, or variability. We've got our sum of squares. Error is variability within each condition or group, okay? This is our variability within groups due to individual differences in error. We calculate this as the sum of the squared deviations of person I in group J from group J mean, right? So in this situation, it's going to be 0 minus 1, 3 minus 1, or 0 minus 1 squared plus 1 minus 1 squared plus 3 minus 1 squared plus 1 minus 1 squared plus 0 minus 1 squared. That's going to give me my sum of squares for here, plus 4 minus 4 squared, 3 minus 4 squared. We're just looking at the squared, some of the squared deviations within groups. That's going to be my sum of squares error. This is stuff that we haven't accounted for in the model, so it's just stuff that's unexplained. Okay. And then we have our sum of squares treatment. This is the variability that we get after removing our within group error. So we can talk about this as the sum of the squared deviations of my group mean minus my grand mean squared multiplied by the size of my sample, or I can get there by subtraction, right? If this is the total variability in the model, and I pull out the variability due to within subject stuff, what I'm left with is my between subjects variability. Okay. Then what I can do is I can take those sum of squares and I can divide them by a degrees of freedom estimate, which gives me a mean squared treatment. Remember that mean squared in ANOVA speak is just a variance estimate. Okay, I've taken a sum of squares divided by a degree of freedom. It gives me a mean square. It's just a variance. Okay. And then to get my F test, I take my mean squared for my treatment over my mean squared error. Gives me my F ratio, and I'm off to the races with stuff. Okay. Now, are people comfortable with sort of understanding where these variance components are coming from? Because it's going to start to we're going to get crazy as we get into the repeated measures stuff. Okay. All right. So again, here we've got our ANOVA table, our hypotheses, our conclusions, sort of how we go through and just kind of write this all up and think about this. Again, this is all stuff that we covered last semester, but just want to kind of freshen it up in your mind, to sort of put you in the right space as we start to get into sort of repeated measures things. Okay. So that was our between subjects ANOVA stuff. But we also want to go through and touch base back on repeated measures. Okay, our repeated measures designs are what we're typically doing, almost always doing here, is we're looking at the same group of participants on one or more variables across 2 or more occasions. Now I have that asterisk. Who can remember sort of when is this not the case?
Is it when you match the participants?
Yeah, if I've got a matched design. By convention, we would use repeated measures approach to a matched pairs design, but almost always, particularly, just don't see a lot of matched pairs stuff. And if you do, it tends to be a more complicated analysis. So we're almost always going to be talking about some situation where I have a sample that I've measured on 2 or more occasions. Okay, benefits of my repeated measure. They map really well onto a lot of the types of things that we're interested in psychology, right? How do things differ, or how do patterns change over time? It's just a lot of what we do, right? So it's kind of a nice, conducive design. They're more efficient. I need less people to be able to go through and do it. Instead of having 3 different samples on 3 different occasions, I can just have one sample and measure them 3 times, right? And the big thing from a statistical standpoint that's helpful is I can start to control for just random stuff, right? So let's say Robert tends to just gravitate towards the high end of a scale. You give him a scale, so he likes big numbers. He likes to report towards the high end of the scale. Basha is a minimizer. She's down at the bottom end of the scale, right? Now, if I'm just looking at Basha's measure and Robert's measure, I'm seeing differences there, right? But there's no way, if I only measure them once, I can't sort of start to differentiate out. So what's that true? How much of that is true score, and how much of that is just how Basha and Robert approach responding to different things. However, if I've got Basha and Robert measured on 2 or more occasions, what I can start doing is I can start taking variability that's due to individual difference. I can pull that out and just start looking at sort of the systematic differences across how they're responding to whatever it is that we're doing. Okay, and so what ends up happening is we end up with everybody serving as their own control, resulting in a much, much more powerful test. Okay. Now, limitations of our repeated measures designs, carryover effects, right? Again, for clinical folks, if I have want to compare PT or say CBT to some other treatment, I can't bring people in, teach them CBT, and then say, okay, forget that. Now you're going to do this other thing. They have that. And so the repeated measures design starts to be sort of problematic if people can't unlearn what they just did. If you have carryover effects, it kind of takes this out of the mix. We also have some additional model assumptions, some increased complexity that we'll start to get in with these designs. So these are drawbacks, but as long as you're comfortable with that and have sort of found a situation where this can apply, these are going to be really, really advantageous designs to pull in where you can. Yeah. Now, our most simple case that we went through last semester was our paired sample t-test. Again, we're typically using this to look at scores within individuals across measurements. Our difference scores are our primary unit of analyses. My null hypothesis is going to be that the mean difference score in the population is 0. Alternative is the mean difference score is something that's not 0, right? And so essentially what I'm doing is I don't know what the difference between time 1 and time 2 in the population is going to be. So what I'm going to do is I'm going to pull a sample, I'm going to measure it once, I'm going to measure them a second time, and see what differences that we get. In terms of our sample data, remember that the calculation of our t-statistic is calculated as the mean of our difference scores minus our expected value under the null, which is generally going to be 0, so that cancels out, over the standard error of the mean of the difference. Standard error of the mean of the difference is going to be the standard deviation of my deviance scores divided by the square root of n. So in this very simple sample that we've got here, right, we've got 4 participants, scores at time 1, scores at time 2. If we go through, calculate a difference score for each one of these, and then calculate the mean and the standard deviation of the difference score, we've got everything that we need. Okay. And so again, what we're doing with that paired sample t-test, we're asking, the question we're asking is, what's the probability of obtaining a set of different scores with a mean of 3.5, assuming that there really is no difference in the population? Okay. Someone tell me, so what does a paired sample t-test essentially reduce to from a conceptual and a calculated and a mathematical standpoint?
Single sample t-test.
Yeah, it's just a single sample t-test of your difference scores. Okay. All we're doing is we're just saying that you can take these difference scores and run a single sample t with just these against a null value of 0. It's going to give you the exact same test statistic and p-value as your paired sample t. Okay. So this gets us to our repeated measures ANOVA. Okay. With our between subjects designs, we're assuming that all of our individual cells are independent and uncorrelated with one another. Okay. I've got treatment 1, I've got treatment 2, I've got treatment 3. In a between subjects design, I'm assuming that the scores I'm getting from participants in treatment 1 are completely independent from the scores that I'm getting in treatment 2, are completely independent from the scores I'm getting in treatment 3. Within each sample, we're independent of one another. Across people, we're independent of one another. And so because of this, I'm expecting that the correlation between my treatments have an expected value of 0. Mean for treatment 1 should be uncorrelated with mean for treatment 2, should be uncorrelated for treatment 3, because they're all different people, right? Again, it's this independence, our between subjects stuff all falls on this independence, all is based on this independence of subs assumption. But let's say instead of different participants in each condition, we had the same people in all 3 conditions. Okay. In this situation, we've got participants 1, 2, 3 to n. First, they complete manipulation 1, then they complete manipulation 2, and then they complete manipulation 3. In that case, would we expect that the results of treatment 1 would be uncorrelated to 2, be uncorrelated to 3? No, because we've got the same people performing across each one of these. So what we've essentially done is we've introduced a correlation into each one of these treatments, okay? And generally this is problematic, right? For an independent sample design, let's say, Robert, you've got your thesis right now, right? And you're having people walk through and sort of complete so these mindfulness tasks and things along those lines. Would you be upset if you had, say, participant Bill scores were related to participant Frank's scores? Yeah, that would be problematic, right? Because I would have dependencies across this, right? Emily, this is if I'm doing school-based stuff, right? If I'm measuring all the kids from class 1 and all the kids from class 2 and all the kids from class 3, the problem is I've got dependencies there, right? Because two kids in class 1 are probably more similar than a kid in class 1 and a kid in class 2, right? So we've got dependency. This is generally sort of a big issue that we need to be thinking about. Same thing, Amanda, if you're looking at, again, we'll go back to confidence and guilt, right? And I've had people work in juries, but then I'm just going to throw them all together and pretend that those are all independent scores. They're not, though, right? Because the confidence of guilt is probably going to depend on the jury that they're involved in. And so I've got dependence in there. And so all of a sudden, so the assumptions of my independent sample test is hugely violated, and so I've got some problems with this, right? But when we do it in a systematic way in our repeated measure design, right, what we've got is we're allowing those measures to be explicitly correlated. We expect it, we know it's in there, and we're modeling it. And so because of that, what we can do is we can start to go through and parcel out the differences that we're seeing due to individual sort of just because we've got different people in the sample and different people are different, versus the stuff that's systematic across repeated measures. And the individual difference piece, right? That's such a big part of your total variability in your outcome, right? And it's never anything that you're going to be able to account for. Is there any way to account for why everybody is going to be different than some other person? No. There's just a ton of stuff. And so what that ends up introducing is a huge amount of variability that's unexplainable in our data. And when we have unexplainable data in our data set, what does that do to our tests for systematic differences? It impacts the power, right? Because we've got a whole lot of static in the system, and it's static in the system that we can't account for, right? But if we start to measure people over multiple time points, what we can do is we can say, hey, Matt tended to respond this way, which was similar to the way you responded this way, which is similar to the way you responded this way. What I can do is I can start to parcel Matt's individual differences out. And what I'm left with across individuals is the stuff that's more closely related to the repeated manipulations that I've administered, as opposed to just random garbage that makes Amanda different than Robert, than different than Emily. Not that the things that make Amanda different than Robert than Emily are very special and important things. It's not random garbage, but from a statistical standpoint, it's random garbage, and I don't like to have it in there because it muddies up the waters. Okay, so this is the power of these repeated measures designs. Okay, all right, we'll stop there, and we'll start to get into some examples of exactly how this kind of works out next week. But questions about what we've gone through to this point, what things are looking like, where we're at with stuff? Okay, cool. So we've got problem set 1, which will be due this coming Friday, not this week, but the following week. Okay. It should be pretty straightforward, although like with any of these, there are things that can get a little bit tricky. Okay. So make sure to take a look at that, get a head start. We're not going to be using any data. I'm going to have you do some conceptual problems, some hand calculations, create an Excel calculator and stuff like that. So again, like first semester, it's kind of a nice sort of entry into stuff. So just make sure to get a start on it early. Make sure that collaborate, work together, but again, remember that all interpretations need to be done independently of one another, right? So you can say, okay, hey, we think about this and that, but as soon as words start coming out of mouths and going on pages, that needs to be separate from one another. CJ and I will be available if anything kind of goes sideways or goes wrong, but I think sort of based on the stuff that we figured, sort of worked on, you should be able to figure it out. Just make sure that you're reading that HAL chapter and the Steiger paper and the Meng paper before you jump into trying to do stuff. Otherwise, you'll be turned upside down. It'll take longer to figure it out than if you would have just read the paper in the first place. So, sound good? All right. Any questions? Yeah. I posted it yesterday, so it's up in the problem set folder there. So.
Okay. My folder is empty, but I can figure that out.
I'll go through and I'll check after we get off to make sure that's up there. I thought I did it yesterday, but who knows? So I'll go through and check. What's that?
Mine was empty too, so I don't see it.
Okay, I'll go through and make sure that it's set up. Okay, awesome. Any last questions, folks? Yes.
Sorry. You might have said it in the beginning of last class that wasn't recorded. Is it still Friday at noon? Right?
Yeah. Same thing as last time. Same situation. Same song and dance. You will all have it under control. So yeah, just Friday at noon in CJ's box.
Cool.
Yeah. All right. There's the man. Right. CJ, anything to add or sort of things for people to be thinking about?
Nope, I don't think so.
Okay.
Covered it.
Awesome. Cool. All right, folks. Well, good luck. Let us know if we have anything that comes up. Otherwise, enjoy your rest of your afternoon.